Welcome back to our ongoing deep dive into the OEIS. As any number theory student knows, this database is just an absolute treasure trove of fascinating sequences. And today we're taking a closer look at A000103, a sequence that really gets right to the heart of some pretty interesting topological and combinatorial questions.
Yeah, that's right. It might seem simple at first glance. A000103 is all about the number of ways to triangulate a sphere, with the added condition that each node in the triangulation needs a degree of at least 4. But as we kind of dig deeper, we'll see that this seemingly straightforward setup leads to some really surprising complexities.
Okay, so let's unpack that a bit. I know our listeners are familiar with triangulation, but just to make sure we're all on the same page, could you remind us how it works in the context of topology?
Sure, you can think of triangulation as taking a space like our sphere here and dividing it up into a network of triangles. It's essentially about replacing a complex shape with a collection of simpler shapes, these triangles, to analyze it more effectively. And these collections of triangles form what mathematicians call simplicial complexes, which are really fundamental tools in topology.
Now, A000103 isn't just about any old triangulation, right? It has that special rule about the nodes.
Exactly. The sequence specifically focuses on triangulations where every point where those triangles meet, each node, has at least 4 edges connected to it. It's this constraint that makes A000103 so interesting.
So let's jump into the sequence itself. The OEIS entry gives us the first few terms, 001125. But wait a minute. Why are those first two terms zeros?
That's a great question, and it highlights how this degree constraint really changes things. Imagine trying to build a structure out of triangles where every vertex has at least 4 edges. You quickly realize it's much trickier than it sounds, and that's the essence of what A000103 is quantifying. Those tricky structures.
I'm starting to see how this sequence gets complex fast. Those initial zeros tell us something important about the limitations this degree constraint imposes on the possible triangulations.
Precisely. If you think about the simplest 3D shapes, like a tetrahedron with 4 nodes, or a 5-by-pyramid with 5 nodes, you simply can't triangulate them in a way that every single node has a degree of 4 or more. You'll always end up with some nodes having only 3 edges. And that's why those first few terms of the sequence are zeros. You need at least 6 nodes to even have the possibility of fulfilling that degree 4 requirement for every node.
So those zeros aren't just placeholders. They're telling us something fundamental about the relationship between the number of nodes and the possibility of creating these specific types of triangulations. It's fascinating how such a seemingly simple rule about the number of triangles meeting at a point can have such big impact.
It really does highlight the elegance and complexity hidden within these seemingly simple mathematical concepts. And that's one of the reasons why the OEIS marks this sequence as hard. It's not just about counting triangles, it's about understanding how this specific constraint drastically limits the possibilities, and how those limitations play out as we increase the number of nodes.
It's like we've turned a simple geometry puzzle into a deep dive into combinatorics and topology. I'm already intrigued to see where this goes. But before we move on to the later terms in this sequence and what they can tell us, I think it would be helpful to take a closer look at an example of a triangulation that does satisfy this degree 4 condition.
Absolutely. Visualizing it can make a world of difference. Let's consider a simple example with 6 nodes.
Okay, so we're picturing a sphere, and we need to divide it into triangles, making sure that every point where the triangles meet has at least 4 edges connected to it.
Exactly. One way to do this is to imagine a cube inscribed within the sphere. Now, if you connect each corner of the cube to the center of the sphere, you've essentially divided the sphere into 6 pyramids, one for each face of the cube.
I'm visualizing it. Each pyramid has a square base formed by one face of the cube, and its apex is at the center of the sphere.
Precisely. Now, to turn this into a triangulation, we simply divide each of those square bases into 2 triangles.
So now we have 12 triangular faces on the sphere, and each node, whether it's a corner of the cube or the center of the sphere, has exactly 4 edges connected to it.
Exactly. This is one valid triangulation of a sphere with 6 nodes where every node has a degree of 4. And this visualization gives you a sense of why those first 2 terms in the sequence are zeros. It takes at least 6 nodes to even make this kind of triangulation possible.
This example really clarifies things. But I can already imagine that as we increase the number of nodes, the number of possible triangulations, even with the degree 4 constraint, is going to explode.
You're absolutely right. The complexity grows rapidly. That's where tools like the SurfTri program come in.
Right, I remember we touched upon that earlier. The OEIS entry mentioned SurfTri. It stands for Generating Triangulations of Surfaces. Could you elaborate on how this program helps mathematicians explore A000103?
Absolutely. SurfTri is a powerful computational tool that allows mathematicians to generate and analyze triangulations of surfaces, including spheres. Based on specific criteria like the degree constraint we're discussing, it can systematically explore a vast number of possible configurations and identify those that meet the requirements of A000103.
So for number theory students who are interested in digging deeper into this sequence,
Yeah.
SurfTri sounds like an invaluable resource.
It is. And the OEIS entry itself provides links to this program and related research, making it easier for anyone to delve into the complexities of A000103.
That's one of the things I love about the OEIS. It's not just a static database. It's a dynamic gateway to a whole world of mathematical exploration with connections to tools, research papers, and related sequences. Speaking of which, the entry also mentions some interesting connections to other OEIS sequences, doesn't it?
It does. For instance, it links to A000109, which gives the total number of ways to triangulate a sphere with n nodes without the degree 4 constraint. Think of it as the parent sequence to A000103.
So A000109 gives us the bigger picture of all possible triangulations, and A000103 zooms in on a specific subset, those with the degree 4 constraint. That's a really helpful way to understand the relationship between them. Are there other related sequences worth mentioning?
Yeah, there's A081621, which focuses on triangulations where the minimum degree is 5, making it an even stricter subset within the world of sphere triangulations.
Wow, so we're going from all possible triangulations to those with at least 4 edges in each node, and then to those with at least 5 edges. It's like we're adding more and more layers of complexity,
Right.
and each layer has its own sequence in the OEIS.
Exactly, and that's what makes exploring the OEIS so fascinating. It allows you to see how these seemingly specific sequences are actually interconnected, revealing deeper patterns and relationships within the broader field of mathematics.
It's like each sequence is a piece of a larger puzzle, and by studying them individually and in relation to each other, we start to get a clearer picture of the whole.
Precisely. And in the case of A000103, it's not just about the numbers themselves, it's about the questions they raise. How does this degree constraint impact the growth rate of the sequence? What can these numbers tell us about the underlying geometric and topological properties of these triangulations? There's so much more to uncover.
It's a great reminder that even seemingly simple mathematical concepts can lead to profound and unanswered questions.
Absolutely. And for any number theory students listening, I encourage you to dive into the OEIS and see what other connections and patterns you can find. You might be surprised by where these explorations lead you.
Well said. So as we wrap up our deep dive into A000103 today, what's the key takeaway you'd like to leave our listeners with?
I think the most important thing to remember is that A000103 is a window into a surprisingly complex and interconnected world of mathematics. It highlights how constraints can dramatically shape the possibilities, and how seemingly simple rules can give rise to intricate patterns and structures.
It's a testament to the power of observation, exploration, and that constant drive to find connections and meaning in the world of numbers.
Couldn't have said it better myself.
Thanks for guiding us through this fascinating deep dive into A000103.
It's my pleasure.
Until next time, keep exploring the OEIS and all the wonders it holds.